Hi, my name is Christina from Group 93, and today, as the owners of Use Case 3 of Riga case, we are presenting the final demo of trip characteristics inference and traffic flow data analytics. Use Case 3 focuses on public transport data management and analytics. But before going into technical details, I want to mention a few challenges. The city uses a check-in only system, and data so far is mostly used for general statistics. Limited capacity to store and process large datasets makes it harder to understand real travel patterns and demand. That brings us to the visual representation of the final deployment of the use case. We will further demonstrate it step by step through three pipelines, starting with the first one, or optimization of existing public transport network, which focuses on supporting transport and urban planners to analyze passenger behavior to better understand travel patterns and preferences. Here you can see the GTFS real-time data viewer, one of the three datasets needed to run the trip chaining algorithm, and the only one that is neither stored by the city nor available through the Latvian Open Data Portal, mainly due to its large data scale. There are two ways how to download the data. The first one is simple option where you just select the date and hour. The second one allows bulk download, letting you choose a specific period. In this case, we selected July 2024 as it is the main period we focus on throughout this demo. Scrolling down, we can see a data preview, data schema, and visualization of vehicle positions as data points. There's also a nice feature that lets you view how vehicles move during a specific hour in space at that time. Next, we will switch to the Python window where we will run the trip chaining algorithm that fuses three datasets, GTFS real-time, static GTFS, and e-ticket validations. It takes a quite time to process, so let's jump straight to the results. Here is an example of how the results look in Excel. We have information on the date and time, trips and vehicle IDs. Of course, we can also see all the details about the entry stops. There's an extra column showing the delay between e-ticket check-in and the GPS track. And then the most interesting part, the exits that were successfully determined. After analyzing and aggregating the data, we can also visualize it, for example, in QGIS. Here you can see how the ODs look at the public transport planning zone level. Let's take one of the zones as an example for a closer look, say the Latgales neighborhood central area. And what we can see here are all the destination zones and the number of trips made to each of them. After running the trip chaining algorithm, we move to the drop-off or destination prediction stage. This model uses ticket validation data to estimate passenger destinations, essentially completing the full OD table by filling in what trip chaining couldn't. Here on the screen, you can see the model's output in Excel using machine learning. It identifies patterns between where people check in and where they actually finish their journeys. By aggregating these predictions, we can analyze demand at a broader scale, in this case across public transport zones. And here in QGIS, the same results are visualized as travel pressure. Darker blue areas indicate zones with a net inflow of passengers, while lighter tones show outflow. This helps reveal the main attractors and generators of movements across the city, offering a clear picture of travel behavior. Now we are moving to the second pipeline, prioritizing public transport within the mobility hierarchy. This part highlights Riga's need for a data-driven approach to identify where public transport delays occur most frequently. Trajectory data analytics capabilities work across both desktop and cloud environments, but let's start by going through the process in QGIS. Here we open a ready-made model that extracts information from both GTFS real-time and static data. The workflow begins with trajectory creation, where our GPS points are transformed into movement paths. Then we move to event extraction, which identifies where each trip starts and ends. And after that, we apply trajectory cleaning to remove outliers caused by tracking errors, followed by trajectory generalization to reduce file size by simplifying the data. Now you can see how the final results look. On the screen, we are showing around 30% of all public transport segments, mainly focusing on the central area since that's where the most traffic congestion occurs. From these results, we can observe the intensity of delays at the segment level, even down to the detail of which road experienced delays at specific points along its path. We can also take this analysis further, looking at delays by weekday, by vehicle direction, or even by hour of the day. This allows us to identify clear patterns, such as slightly higher average delays during the morning or evening peak hours. Because of analysis is based on individual trip IDs, we can pinpoint the specific routes and locations where delays occur most frequently. And thanks to such detailed information at the segment level, it's also possible to calculate free flow travel times and compare actual delay against both the scheduled and free flow conditions. Now we move to the trajectory analysis extension in Carto workflows, which operates in the cloud environment. The logic behind how we obtain the results is the same as in QGIS. Here you can see the GPS points displayed directly on the map along with the data preview on the side. If we click on one of the workflows, for example, split trajectories, we can also see an instant data preview showing how the information is processed at each stage. What's great here working in the cloud is that this makes it easy to analyze and visualize delays directly without needing to export or process the data locally. And finally, here you can see the final dashboard where all process results are brought together in one interactive view. The dashboard allows users to explore key indicators such as average delays and segment performance across the entire public transport network. In the map view, we can filter by route, day of the week, or time period to visualize where delays are most common. The charts on the side summarize network-wide statistics, making it easy to identify recurring congestion points or underperforming segments. Altogether, this tool, whether used locally or in a cloud-based environment, helps turn route trajectory data into actionable insights. And that brings us to the last pipeline, fleet planning and management, which focuses on optimizing Riga's public transport operations. In this part, the model predicts the number of entries and exits per zone for a given day of the week and time window. In other words, it forecasts when and where passenger crowds are likely to be denser. The tool is based on open source code. On the screen, you can see the notebook interface. We start by entering the inputs. First, we select the day number. Let's take 2 as an example. Then we enter the time, say 15:15. The system afterwards will highlight and confirm the selected day and time. And then we specify the zone. Here we will use Rumbola as an example. And after running the script, the model outputs the predicted number of passengers entering and exiting that specific zone and time window, providing valuable insights for planning vehicle allocation and improving service efficiency. Here we can see the predicted numbers of passenger entries across different zones throughout the day in QGIS, highlighting when certain areas become busiest over the time. Thank you for listening. I hope these tools and approaches presented here can be applied and adapted across other urban contexts. We'll be happy to share more and exchange experiences. See you in Riga.